Okay, so the first basic thing, when it comes to particles and powders is sampling, right? Subsampling, right? So whenever you characterize or measure some properties, we take small amount of sample, right? Is that right? Yes or no? Okay. I need response. Okay. If not, I will also feel sleepy. Okay. Okay. We'll talk about sampling of powders. Okay. So again, the goal of sampling, and as I said, give an example of wheat milling, right? We'll be milling tons of wheat, but when it comes to measuring the ash percentage or measuring the particle size of wheat flour, we just take like 10 grams or 100 grams, right? So how do we take that 10 gram or 100 gram from that 10, tens of tons of material, right? So that 10 grams or 100 grams, whatever you subsample, should be representative of all the tons of materials you are producing, right? So that's the purpose of sampling. And then again, how do we sample, depend or define your product characteristic too, right? So how many of you do sampling in your lab when you characterize? Do you sample, right? So how do you sample? Give some examples. Come on. How do you so?
We just mix it up properly and then we.
Okay. How do you mix?
Mostly I work with 1 and 2 kg of samples, so we can mix it with hand.
Okay. What sample you?
Rice.
Rice. Okay. Anything else? Any other method that you use? No. No one does sample. Why you all are quiet? Still thinking? Okay. So just give me an example. Okay. So for example, okay. So you would have seen lots of large samples come in large bags, right? So I'm giving an example here, like 250 kilogram of tote bags. Okay, powders coming in 250 kilogram tote bags, but you want 2 grams of particles or powder to measure the particle size using laser diffraction. Okay. So how will you subsample 2 grams from this 500 kilogram? Mixing will be a little difficult, right? Okay. Okay, yeah, that's what 1 gram. You can take 1 gram for each. Okay, but how will you take that 1 gram?
Maybe at different positions.
Okay, different positions. Okay, that's good answer. Okay. Any other thoughts?
After shaking,
Okay, shaking. How do you shake? Do you need a very large shaker for this, right? Manual?
with a spatula we can take some.
Yeah, spatula. Yeah, that's the common sampling procedure that we use, right? Just use a spatula or spoon. Just take 1 gram, right? Okay, so we'll talk about that methods. Okay, what disadvantage, advantage, of these methods have. Okay, and we'll talk about different sampling methods. Okay, so when you go to any process industry, in general, we see different types of sampling. Okay, outline, inline, online, offline sampling, etc. Okay, so online usually you don't remove the sample. Okay. So for example, again I'm going back to wheat flour, wheat milling process, the flour will be still in the pneumatic handling system, but there could be a laser diffraction or laser system that measures the size of those particles, on the floor. Okay. So those are, online is very common nowadays. You would have seen many, industries using NIR, near infrared systems, so that you don't have to take the samples out. On the floor you measure the characteristic. Okay. Outline is very common, that gives more that helps with a little bit more advanced understanding of the particles. Okay. So again, online systems, in general, we cannot, characterize them using their direct property. Most often we use their indirect properties like, near infrared, optical property, those are very common. So those are like not direct properties. So but at line, we will be able to, characterize them using their fundamental, behavior and fundamental properties. Okay. Offline, most common, when you wanted to do a thorough investigation of their characteristics. Okay, you take the sample, okay, store it, in the lab, and then again, most often you keep the samples for longer duration, like 3 years, 5 years, etc., till you need, the samples. Okay, you would have, you know about grain grading, grain trading, etc., right? So in general, the grain graders, who check the quality of rice and wheat, etc., they keep the sample for like 3 to 5 years. Okay, they measure the quality, but they are supposed to keep the samples for a longer time, since if there is any trade dispute or anything, questions comes up, they want, they will go back and measure the property again. Okay, so those are, helpful in offline measurement. Okay, there are, not, I will not be reading all the verbatim here, but there are more advantages, disadvantages, depending on your process needs. You choose online, or offline systems. Okay. Again, online you use mostly indirect properties to measure, but very quick and easy method of measuring those values. Offline, as I said, it gives very detailed measurement of the properties. Okay. Again, I'm not going to read all these things. There are tons of advantages, disadvantages here. Okay. So again, sampling bias. Okay. So sampling bias is a major challenge, when we subsample powders. Okay. So when you are taking 1 gram, you said you're mixing mixing rice and picking subsample, right? Rice is a free flowing material. So if you mix, they segregate. So that then again that leads to some challenges in subsampling. So you will be sampling a segregated mix. But if you are using a spatula, then again you are sampling an already segregated sample. Okay. So if you are taking from the top, it's already segregated. So you are not getting the property of the exact powder, exact mix of the powder. Okay. So again, as your sample said, you're collecting, samples from a different height. Then most commonly, if you wanted to collect, samples at different height from a large tote bag, we use a probe called thief probe. You would have seen, or you would have used thief probe. Again, that can, destroy the sample when you, insert those thief probes into those bulk bags. That will also introduce bias, in the measurements. Okay. So again, very challenging process, sampling. Sampling. So again, we'll have to take extra care so that we are introducing any bias during, sampling that affect your property measurement or property characteristics. Okay. So again, general, total measured variance, how much variability in the sample, we'll come back to that, towards the later part of the lecture too. So what we are interested is actually characterizing or quantifying the actual variance in the sample, right? How much the property is different. But, unfortunately, we introduce lots of, variance from the sampling, right? If it's already segregated, then you are introducing a bias. And also from the analysis, if your instrument is not calibrated well, if your instrument itself has some error in measurement, then you are adding another variance. So there will be 3 different variants, that we are introducing into subsample, measurements or characterization. Okay. So it's the easiest to control here, which is the easiest bias that we can avoid.
Sampling and the analysis.
Analysis, it's highly dependent, it's not your, issue, right? It's an instrument problem.
You can calibrate the errors.
Most often, but still, you may not know, right? So most often, the maximum variance that you can avoid is the sampling variance, right? If you use appropriate sampling, then you can avoid that variance. Okay, so sampling, that's that's the easiest to avoid. But variance due to analysis also, again, if it's calibrated well, you can avoid, but most often, you will still end up with some instrumental error. Okay. Again, one of the important thing that you have to keep in mind is, you can have an advanced measurement technique, okay, but your sampling is very poor, okay, then you are not characterizing the actual property, right? So you can have like $1 million equipment for measuring particle size, but if your sampling is very poor, then you are wasting your $1 million to measure the particle size. Okay. Okay, so in general, we follow two rules. Okay, when you are sampling. So one is, again, the powder should be in motion when sampled. I thought I had an example before going into this, but I don't see. Okay, I have it in the next part. Okay. So when you subsample powders, you have to keep in mind two rules that you have to keep in mind. One is the powder should be in motion when sampled. Okay, it should be flowing, and the other is many samples should be collected in frequent interval rather than just one sample at one time. Okay. Again, I will go back to the flour milling, wheat milling example. Okay, so if you are collecting, for example, wheat, before it's milled, what we generally do is, when wheat kernels are unloaded from the truck, you subsample when it's flowing from the truck. Okay, you take subsamples and then analyze them. Okay, same thing if you wanted to measure the particle size of wheat flour. Okay, so then you go and collect different samples at different intervals, and then measure their particle characteristics, baking characteristics, etc., etc. Okay, so at least any granular material, any particulate material, okay, if it's a solid, you should keep in mind these two rules. Okay, so why we have to sample them when it's in motion? Why why it's better to take subsamples when it's flowing?
That will be more uniform.
Okay.
If that is in motion.
Okay.
The uniformity.
What type of uniformity? Very close answer. Yeah. What type of uniformity you mean?
Density is constant, not
Oh, what is that?
bulk density is constant.
Maybe, not usually, not always. Bulk density can differ too, depending on fluidization conditions. So how much air is there? Okay.
In terms of their size distribution.
Okay. Yeah. Size distribution. Yes.
Particle size also.
Okay. So mainly, if it's flowing, then the chances of segregation will be low. Okay. So when it's when it's stagnant. Okay. So the powder itself would have already segregated, right? So when you subsample from a stagnant powder, then you are subsampling from a segregated bulk. Okay. So when it's flowing, you are avoiding subsampling of segregated bulk powders. So that's why we mainly say sample when it's flowing. Same thing, lots of subsample, so that we are characterizing or collecting powders at different intervals. So if there is some process change downstream. Okay, just again going back to wheat milling example. If you have 6 roller mills, and one of the roller mill, the mill is not very good. Okay, so that might not produce a good quality flour. Okay, so that will come at specific interval, that flour will come at specific interval and mix with the general all the string, powder string. Okay. So if you are taking just one sample, you may not identify the issue in the mill, since you are not gathering sample at that time. So if you are collecting lots of samples at different times, then you might be able to capture the issue with the process itself too. Okay. Okay, again, I ask lots of questions, okay, in the class. That's my style. Okay, make sure again, as I said, there is no wrong answers in the class. Okay, except for Friday. Okay, So again, that's the objective is to make sure, the subsample that we are collecting is representative of the bulk of material that we are, producing or shipping or handling. Okay. Any questions so far? No questions? Yeah, go ahead. Yeah, go ahead. I will come back. Yeah, go ahead.
Sir, how to sample from bags like
Okay, the large bags. Okay, we'll talk about that in a minute. Okay, good.
Should locations also vary with the in the stream?
Yeah, locations will also vary. Yes, yeah. So we'll have to, depending on the objective of your process, we'll have to find a location appropriate, a location within the process that gives your, objective. Okay. Any other questions? No? Okay, so we'll move on to the next part. So we'll talk about some sampling methods and equipment. Okay. So one example here. Okay. So a powder is transported by a conveyor belt, and the powder, it's discharges into a drum. Can you describe an appropriate sampling procedure? How do we sample powder when it's flowing? And again, it satisfies the first rule, right? The powder is flowing, you are sampling when it's flowing. Okay. So can you develop an appropriate subsampling procedure for this system? How do we sample the powders?
So, as it is flowing, it is maintaining the
Okay.
first rule, and for the second rule, we can take from different positions
Okay.
1 gram or
Okay.
something,
Okay.
material, and then you can do the sample.
Okay.
This all the time.
Okay. So very good. So you'll have to, one condition is applied, satisfied, right? You are sampling from the flowing stream, right? Then how do we, one minor change in that answer will be okay. So you cannot collect from different locations, okay? So it's flowing from the powder, okay? So if you are collecting from different locations, what happens is you are, when it's flowing, there could be some, differentiation due to changes in density, okay, or particle size, okay. Sometimes the larger particles will flow differently than smaller particles, right. So if you are picking, from random locations, you might get a segregated mix still, okay. So what we have to do is use a large container, okay, and then run it through the flow stream, okay. But again, this is a bad subsampling procedure. So you cannot run the container, to and fro, back and forth through the flowing stream, okay. So only one motion, okay. So this is wrong, but either take the container through the stream from front to back, so you are getting all the segregated mixtures too, okay. If not, from side to side, okay, one side to the other side, okay. So again, you are gathering all the segregation or possible, segregation within the stream when it's flowing into the, container, okay. But again, if you are running it back and forth, then you are collecting a segregated mixture, okay. So there could be some segregation of the powder within that, subsample, okay. And again, sample stream at multiple random times. One of the important thing that you will have to keep in mind is if you are using a container, the container opening should be greater than equal to 20 times the particle diameter, okay, so that you are not losing any larger particles, all the particles are falling inside, okay. Again, you don't want the container to be full when you are sampling. And again, why means, you don't want any overflow from the container, okay. So, make it's full till 3/4 of it, and then, use it for subsampling, okay. Any questions? Okay, we're getting lots of examples from food, right? But agriculture, your students in agriculture, right? So, you should also give some examples, okay, when I ask questions, okay. So you joined late, so can you introduce yourself to the class? Okay.
manufacturing food.
Okay, so what's your research on?
My research is on hydrocolloids effect
Okay,
on pea protein based meat analog
Okay.
for extrusion technology.
okay, great, yeah. Okay, so again, another option is, you stop the belt itself, okay? So if you stop the belt and then use some cutter sample, there are, you can get these in markets, sample cutters, use some sample cutters or sample dividers and gather samples from multiple portions within the belt, okay? Though it's not, satisfying the first rule of sampling, it's not flowing, but still you get different, mixes of powders from different locations, okay? So that will be again, a good approach. There are again tons of different sub-sampling systems. In any of you been to a bulk, production facility? No, mostly, particulate material like fertilizers, soil, mines, mixing. So you might see one or other type of, sub-sampling, systems in those bulk production facilities. Common one, collection chutes. These are very common. Yeah, sampling. These kind of containers back and forth that pulls sub-samples. And those are very commonly used sub-sampling systems in bulk material production facilities, okay? And there are tons of systems, many methods available, okay? So as I said again, it's a large, if you are sampling from a large container, you should avoid because it's mostly already segregated. So what you are collecting is already a segregated mix of powder. So the option that we usually, what pharmaceutical industry at least does is, if they wanted to subsample from a tote bag, like a 250 kilogram bag, they pour it into another container, okay? And again, so you are, satisfying the first condition, the material is flowing, right? When it's poured, then they subsample from multiple locations when the material is flowing from the tote bag into another container, okay? So if you cannot do that, then use some thief sampler or other subsamplers and collect samples at different locations within the, within that tote bag, okay? So that's one, if you cannot avoid. But again, we always use, scoops, ladles and stuff, right? We'll talk about that in a minute, okay? So why sampling again is a problem? Again, segregation, you would have seen this picture a lot, in internet, right? So bulk powders, they segregate a lot, right? So it can segregate based on the difference in composition, difference in density, difference in size. Lots of properties influence their segregation. So if you are taking sample from the surface, for example, if you're picking like scooping from the surface, you are not gathering the powder from inside. So you are getting a segregated bulk, okay? So that's again, that should be avoided. Same thing for, when you are, transporting bulk material in trucks and containers. Usually, so which material, okay, I have the color there. Lighter material comes to the top, right? Do you guys know the name of that effect? The name of that effect. Why smaller, lighter materials come to the top when you're, okay, so do you know the name of the effect? Buoyancy, yeah, but there's a particle name, for particle segregation. Okay, you might have not heard. So it's called the Brazilian nut effect. Okay, so you might, if you just Google YouTube, there are tons of videos, Brazilian nut effect. So larger particles, or lighter particles, segregating. So in general, larger particles come to the top, and lighter materials, again, come to the top. Okay. You all would have seen, nut bags, right? Nut mix that comes in small plastic bags, right? Nuts, peanuts, other types of cashews, etc., mixed in a bag, comes in small bags. Usually, when you see those bags, the larger nuts, for example, cashews, will be in the top. The smaller nuts will be in the on the bottom, right? So that's again, differences in size that leads to this segregation. Okay. But again, going back to the nut bag example, okay, how do you avoid segregation of those nuts within a bag? They do add some other materials inside the nut bag so that they don't segregate. Any guess, any thoughts? What material they add to avoid segregation in nut bags? No? Any quick guess? No? So, most of the nut bags will come with raisins nowadays, right? Raisins, dried grapes. So, raisins are cohesive, so they avoid segregation. So, they keep the materials in place. Okay, that's again, they add it as healthy too. But, so going back, we'll talk about those segregation, Brazilian nut effect later on. Okay, so again, if it's based on density, based on sizes, the materials segregate. And if you scoop or take small amount of sample, what you get is a biased mixture. So that's why we avoid, we try to avoid static sampling and also using scoops and ladles. Okay, but scoops very easy, right? You just go and scoop, right? But if it's not avoidable, then again we can still use, many people we still use in industry. Okay. But couple of things to keep in mind, again, don't allow the samples to overflow when you're scooping. So when it's overflowing, what happens? The larger particles will roll off. Okay, so you might not get an accurate, again, accurate mix of the samples from the bulk. Okay, but it's scoop can be used if the particles are cohesive or the material is cohesive. Cohesive materials don't segregate, right? So if they don't segregate, then you can use scoop. You don't have to worry about segregation. But if it's free flowing materials like grains, free flowing powders, larger size materials, then scoop is not a better or ideal method for sampling. Okay, because they segregate a lot. They lots of other factors that leads to segregation. Okay. Thief probe, again, it's very common. If you cannot make them flow, if you cannot take subsample from other means, you can use a thief probe. Thief probe means long probes, either with multiple pockets inside or one simple. Again, usually the probes will have pockets depending on the type of powder and orientation where you want to sample. Okay. So you collect samples from the ideal location or from multiple locations and then mix them together and then subsample. Okay. It's very common in large storage structures if you cannot subsample. For example, if you are large grain storage structures, grain bins, large structures where we store fertilizers, etc. You cannot use any other subsampling. Okay. So you'll have to use these kind of thief probes or pocket probes, etc. Okay, again, very easy to use, simple to use, but again gives a decent amount of subsamples from the bulk. Okay, so far at least it's if it's if it has some periodic segregation issues, then one of the research said for at least for pharmaceutical powders, if you use an N sampler, that gives a better result than these kind of samplers with multiple pockets. Okay, or one subsampling at the end might give a better result of subsampling than other devices. Okay, I'll skip this one. Okay, so sampling from trucks and rail cars, in general, this from again Canadian Grain Commission. They suggest to sample from at least 8 locations within the rail car or within the truck. Okay, so if it's manual sampling, it will be a little challenging, but most of the grain handling processing facilities nowadays have the automated pneumatic samplers. I will show you a picture in the next slide. Okay, that goes till the bottom of the truck. Okay, so what happens is again before these pneumatic sampling systems, okay, So manual sampling, we cannot sample till the bottom of the truck, right? So what people do is they put the poor quality stuff at the bottom and fill it with good quality on the top. So when they subsample, you get the good quality material on the top for getting better price. So but now they cannot avoid, since with pneumatic systems they can go till the bottom of the truck. Okay. Again, pneumatic, very similar to the thief probe, but it operates based on using pneumatic like suction principle. So the probe goes to the till the bottom of the truck and then sucks samples at different heights, okay, and then gets the quality. Very, very simple and easy to operate. Okay. There are other sampling equipments too, little high end, we may not use in food and grain processing industry, but there are X-ray, gamma ray, NIR, NMR systems that can these are mostly used for inline and outline measurements. Okay. So use them and then take you don't take subsample, but measure the sample at in the process itself and then characterize them. Freezing a sample is another option. Again, these are mostly used for high value products. If it's very expensive, most common in pharmaceutical process. Even in pharmaceutical industry, 1 gram itself is very high value, right? So they use these kind of high end subsampling procedures. Freezing, again, adding liquid binder, then freeze them, that portion, and cut them, so that you save the integrity of the sample till you analyze. You are not adding any additional segregation, adding any other, you are not breaking the sample, etc., while handling and taking to the measurement unit. Okay. Okay. Any questions? Go ahead. Yeah.
So for the truck and breakers, you said that the pneumatic system will be used for this. What will be the state of the car or the truck where the grain is being stored?
Oh, it will be idle.
It will be on steady state.
Yeah, in steady state. So what happens is in at least in the industry, so near the gate when the truck comes in or even rail car comes in, they stop at the gate, then they pull sample. The truck will be idle, they pull samples at multiple locations, then they measure the quality. Based on the quality, they choose where to send the truck.
But truck means that is tons of material.
What's that?
If truck means the tons of material, they will reject the whole truck.
Yeah, they will reject the whole truck. Or they reduce the price. They could reject, they could reduce the price. If the industry wants more sample, they can do additional processing. For example, if it's high moisture, then they send it to the dryer to dry it down before storing. So they choose based on the quality, like starting from price and where to send the material. Okay.
Okay, and there is one thing
Yeah.
for the freezing one. The freezing is done before sampling,
Yeah, before sampling. So
just to restore the shelf life of the product.
no, not for shelf life. So when, for example, if the material is coming in, a belt conveyor system, okay, if you are subsampling, still there will be some segregation, there will be some particle breakage, etc., right? If you don't want that to happen, you stop the belt, add some liquid binder, for the material that you wanted to sample, and freeze them, and then cut them and remove. So you preserve the integrity of the sample as such.
Okay. And during the sampling, that will be in freeze state.
Yeah.
Okay.
And then you take it out, then you analyze the characteristics.
Okay, sir.
Okay.
Thank you.
Okay. Problem. Good questions. Any other questions? Go ahead.
The image you showed for the truck sampling, there is the probe where 10 degrees Celsius is shown. What is the significance of that inclination angle? That 10 degree?
So usually that's easy to go and say. That's a good question. So just for penetrating that tube to inside the grain mix. Okay. So if you are vertical, again, mostly if you have lots of impurities, then vertical immersion of this probe will be very challenging. So it goes little slanting. And this is for one system, 10 degrees, it's not always fixed.
Okay.
Okay, yeah. And depend on the type of grain, type of material, etc.
Okay.
Okay, good. Any other questions? Okay, move on to the next one. Okay, so sampling scheme, sample size reduction. So again, we will talk about that. I believe we will do some again. If you have calculator, we will do some calculations too. Okay, so there are three different types of sampling schemes the industry use. Okay, one is kind of pure random sampling. Okay, so I'm giving example of belt here, but it's common for any type of process. Okay. So random sampling, if the material is flowing in a belt, you just pick it, just go randomly. I go at 10 o'clock and then I sample powder, then again I go back at 2 p.m. and then collect some sample, then I might go again at 2:30 and then collect some. So it's completely random. Okay, but again some sampling, some industry use systematic sampling. Okay, at every hour, every top of the hour I go and subsample. Okay, so 12 noon, 1 p.m., 2 p.m. I go and subsample. That's again systematic sampling. The third, little bit better approach might be, again depending on the process, is stratified random sampling. Okay, you fix the period. Like if you want to sample once every 2 hours. Okay, you fix the time period like 2 hours. Once every 2 hour time window, I need a sample collected. Okay. But within that 2 hour window, you don't fix a time, you go at any time within that 2 hour window. Okay? So it's randomized within that 2 hour, but every 2 hour you go and collect a sample. Okay? So these three are very common, again random, completely random, again systematic, so you fix the time, and then random stratified. So random and random stratified are very common, but systematic, it's not very common because it might not capture sometimes, it might not capture the, process changes that are occurring within the, within the process stream. Okay, that might not be very accurate, but most common is random stratified, but random is also. Okay, and again, handling bias. So you take sample, right? So you will have to analyze them, right? So you take sample, you have to transport them to your lab or to any facility, right? So during handling, there could be some bias, like, it could segregate, right? So as you said, you are producing tons of wheat flour, you are collecting 1 kilogram and then bringing to your lab here, okay? So while handling, there could be some segregation of material, right? So within that 1 kilogram, or particle breaking, change in condition. For example, you're collecting, is it usually humid here in this place? So high humid, but if you're collecting some sample from low humid regions and then bringing it here, so the humidity, temperature will also change their properties, right? So you are introducing some additional bias during those handling process. Okay, then again, one of that not always common, not always possible, but what we suggest at least for industry is, you have the process similar. If your production process is in a high humid condition, then you do the characterization in also in a high humid condition. Okay, because if you are measuring at low humid conditions, it might not exactly replicate the particle data that you will see at high humid process conditions. Okay, but that's again, not always common, but it's always suggested if you are working in an industry. Okay, so scale at what's the scale of sampling or subsampling or scrutiny that is needed. Okay, so when you for example, when you increase the scale, your uniformity goes up, right? But when you reduce the scale, your uniformity might go down, right? So the scale will, again depend on your process. For example, again, just an example, if you take this black dots and white, squares, if you take a larger scale, then it almost gives a uniform mixed indication, right? But if when you take a smaller scale, okay, so there is no mixing at all, right? So the scale will depend on the process and the product that you are manufacturing, okay? I've given a couple of examples here, right? You know, if you're making a compact or pharmaceutical tablet, your scale should also be same as the size of a, you know, pharmaceutical tablet, okay? Or if you're making a roti, okay, from wheat flour that we have been talking about, okay? So your scale should match the amount of flour that is, you know, needed to make a roti, okay? Like 50 grams means, I don't know how much we need for a roti, but I'm just throwing out a number, right? If 50-gram sample powdered wheat flour is needed to make a roti, then your scale of scrutiny should be 50 grams, okay? So 150 gram, taking 150 grams might not give the exact replication of what you needed, because since you are interested in the quality of roti, okay? Same time, if you are taking like 10 grams measurement, then it's not needed. It's very small, which is wasting your time and energy and effort, okay? So the scale of scrutiny usually, you know, should match with your process needs, okay? So in general, you know, when we are talking about process, again going back to wheat flour milling, you know, we will be manufacturing, you know, tons and tons of wheat, you know, wheat flour, right? That's in the process scale, but you know, for analysis, we might bring some in sample scale, right? Tens of kilograms or a small tote bag, right? But when we use for testing, we take very small amount, right? For example, particle size, like you take 2 grams from that tens of kilograms, right? So we always have to subdivide the sample, right? So from tens of kilograms to couple of grams, right? So the tens of kilograms is the subsample that you collected from the large process, but still you have to subdivide for, you know, matching up with your scale of measurement, right? So always we'll have to subdivide the sample, right? So can you guys give some example of instruments that we use for subdividing, at least for grains and food? So when you take subsample of rice, you know, sample of rice, how do you subdivide?
Based on the indented cylinders.
Okay, no, do you use any instruments to subdivide the sample? No, okay. Anyone?
Measurement cups are there
Okay.
for household purposes.
Okay. Yeah, okay, it's around like scoop, right? Yeah, you're scooping out samples, subsamples, right? Any other instrument that you would have seen? No? What's that? Sieve shaker, that's not for subsampling, you know, but you know, it's for mostly size measurement. Okay? At least for the people from, you know, who are studying here, you should take a walk around your labs, okay, very frequently, okay. There should be a Bonnier divider at least. Any of you seen a Bonnier divider that's used for grains? It should be in the, you know, grain lab or whatever, you know, properties lab. It should be at least. Okay. It's very common. We'll talk about, and again, sample size reduction again. Scoop sampling is okay if you are talking about, or if you're dealing with cohesive powders. If it's cohesive, the chances of segregation will be low, so you can just scoop a sample. So, but again, there will be lots of segregation if it's even mildly free flowing. Okay, if it's free flowing, then there will be lots of segregation. Okay. So one of the, you know, if you do not have any instruments, then one of the method that we suggest is cone and quarter. Okay. For example, you are bringing 10 kilogram of sample and you wanted 100 grams. Okay. So you can make them into a cone and then, you know, subdivide the cone into 4 equal parts, throw 2 of them and mix the other 2, then keep on subdividing till you get the amount of, you know, sample that you wanted. Okay. So cone and quartering again, you know, when the material is flowing into a pile, it would have segregated equally into, you know, different sections within the pile, and then it would have segregated from bottom to top. So that's why you divide them into 4 and then throw 2 of them out and then mix the other 2 and then keep on, you know, subdividing. Okay. That's again one, you know, Suggested method, again, there will be lots of operator bias tools, right? How you make the cone, right? For example, in agriculture, if you are, piling lots of soil, so how will you pile the soil? So, and type of soil too, the type, method of piling will, define how you, cone and quarter, right? Table rifler and chute rifler are very common. Table rifler, again, it's again very simple system. You may have one in, here too, or at least in mechanical engineering, or chemical engineering here at IIT. So very commonly used. So you make the powder flow through different streams. So the powder will be flowing, into different streams and collected into different multiple substreams. Okay. So it kind of gets the essence of segregated mix within that powder. Right. Very similar principle like chute rifler. So this is more kind of automated, maybe automated, but again, chute rifler, there will be multiple streams. In a table rifler, the number of streams might be limited, but in chute rifler, there will be multiple smaller streams that collects different streams of powders when it's flowing down. Okay, and then mix them together and makes into a subsample that you can use. Okay. So this is the same principle that you might have seen. Again, you should have one in your food engineering lab. Same principle like a chute rifler and a Bonnier divider. There will be smaller chutes inside the divider, and when the grains or any powder flows through it, those different chutes collects different sections of the flowing material and mix half of that flow into one product, one stream, and then half of them into one stream. Okay. So you keep on subdividing till you get the amount of sample that you needed for your characterization. Okay. So spinning rifler is the most accurate or more appropriate. Okay. I'm using a very old picture here, but there are more advanced spinning or much better looking spinning riflers in market nowadays. Okay. So the same operation is simple. So you make the powder flow through small, a chute or rifle system, and then it flows equally into those smaller compartments. Okay, it flows equally into those smaller compartments. So you are collecting, and these compartments will be rotating. They are not stagnant. It rotates at one constant RPM. So those powders are collected in individual compartments at multiple times, and then you take those subsamples. Okay. Again, for most of the powders, we'll have to optimize the RPM before we subsample that to give a better result. Yeah, vibratory feeders are common. The powders is not very free flowing. Then to make them flow freely, you give some vibration on the feeding chute so that the material is flowing uniformly. Okay. So again, as I said, most commonly the rotary rifler gives a very good result with very low standard deviation of the measurements from the sample. Okay. You can see cone and quartering gives a large variation, but still if you do not have any other instrument, you can still use cone and quartering method. Okay. Yeah, again, I'll skip these advantages, disadvantages. Again, there's one detailed study. You can, it's free to download. If you go into NIST website and or Google Jilla Venkatesa et al. For sampling protocol, you can download the document. So subsampling, we always suggest, for anyone going into the industry, one of the first things that we'll have to do is develop a sampling protocol. Most of the industry may not have a sampling protocol. How you sample powders. Okay. So this again, I'm not going into the study, but what they did was they collected lots of samples and subsamples and mixed them together. Collected and repeated those multiple times, and to find out an appropriate sampling procedure to minimize the errors, or find a sampling procedure with low standard deviation. Okay. So again, I'll not go into the detail, but again, it's freely available in the web. You can just Google and see those details. Yeah. Any questions?
You again have to mix the sample from that particular compartment.
No, you don't have to. So you can keep on subsampling. So this is not sampling, this is sample dividing. After you already sample, for example, you have 100 gram of sample, you want 2 gram from 100 gram for particle size. Then you use that spinning rifle till you get 2 grams. Okay. So this is subsampling. You don't have to do any further division. Okay. Is that clear? Is that clear, or is that okay? Any other questions? Yeah, go ahead.
Sir, is it like dilution usually in evaporation?
What is it?
Dilution.
Dilution. Yeah.
So is it similar like dilution?
Dilution, you are reducing the concentration, right? So you are like, you are not diluting. You are just, for example, if you take, in sugar solution, if you are adding like 100.
Like for finding the number of microbear in the sample, so we dilute it to reduce the sample size.
No, this is, so for example, if you have some, before diluting, if you have like some microbes population, right? So you are dividing those population equally so that, all the microbes are same in all the, whatever subdivision. You are not diluting. It's like subdividing. Okay. Any other questions? No other questions? Are tired? You need a break? Okay, so let's take 5 minutes break. Okay? Is that too short, 5 minutes, or too long? 5 minutes okay? Okay. So let's take 5 minutes break, hopefully before, what time is lunch? 1? 1:30? Okay. So hopefully we'll be done with sampling before lunch, and then after lunch we'll talk about particle size. Okay. So we'll do some calculations now when you come back. Okay. So far is it okay? Are we learning something new? Okay. Go ahead. Yeah. Yeah. Okay, so it's the again T distribution bell curve, so you'll have two tails. Okay, so first thing, for example, okay, so you all have your calculators ready? Okay, so we are collecting 8 samples from a powder to determine its bulk density. Okay, we collected 8 samples. Okay. So determine, first we are not calculating the number of samples, but we are calculating the interval with which in the mean bulk density lies with a confidence level of 95%. So whatever 8 samples that you have collected, you have to be sure that it's accurate representation of the bulk sample. Okay. Okay, so how do we do that? So again, I have the answer. So first thing is you will have to calculate the mean, right? So you know the mean. To calculate the mean, okay, you will have to calculate the average value first, right? So from the 8 samples, okay, then you get the mean, and then again from T values from the T table, students distribution, T-test distribution table. Yes, again, S is the standard deviation that you calculate, again from the given values. Ns, you know the number of samples, that's a number of samples. Then if you plug in all those, you will you get the distribution with 95% confidence. And again, I have values in 3 slides, so you don't have to calculate, but we will do lots of calculations, okay, at least some, okay. So it gives value of about 1.21 plus or minus, it gives about 95% confidence interval of your subsampling, or subsampling, the measurements are within this range, okay. Okay, using statistics, again as said, it can give some closest approximation, okay. So again, from the values, can we use them to calculate the number of samples needed to determine the mean, again, that should give a value of that subsamples that you are collecting for density within 0.01 gram per cc. So whenever you collect some samples, that should give this the mean, the standard deviation should be within 0.01 gram per cc. So for that, values with the confidence interval of 95%. So now you are not collecting 8 samples, but you are just using the standard deviation, okay, or the confidence that you wanted to get to this close, or very approximate characterization, but we need to get the total number of samples that are needed, okay, to get this very exact value, or very accurate value of density, okay. So again, it's the same principle, the t distribution, t test values, standard deviation, the mean and average, okay. So use that, you calculate, again it comes to about 18 samples, okay. So if you collect about, for this example, okay, if you collect about 18 samples, you again, these all are direct plugging in numbers, okay. Plug in the numbers, you get the values, okay. So, but again, so if you wanted to collect them, again, to get the number of samples, it's kind of, you'll have to do some arbitrary calculation. So you'll have to assume a number of sample to start with, okay, because no one asked me that, right. So for t value, you need n value, right. So to get the t value from t distribution value, you need to know the number of samples, right. So without knowing the number of samples, you cannot get t value, right. So we have to start somewhere, with some assumed n, okay. So you keep on calculating, for the confidence interval, okay, or the closest accuracy value at one point, with increase in n, the n prime or your actual value wouldn't change, okay. So at that point, you can take the lowest number or the lowest n value as the number of samples that you are needed to get, accurate value of density, at least for this example, okay. Is that clear? So you start somewhere, okay, with some assumed n value. So you need n value to get t value, right. So you start somewhere and then you keep on increasing, keep on decreasing, then at one point this n prime wouldn't change. So that point, when it plateaus, you take that value as the minimum number of sample needed for characterizing to get good, good close approximation of the density within that confidence interval, okay. And just pure, using statistics, it's very simple, okay. So said it might not give the exact, calculation, but it gives a close approximation, okay. So using those, again, different statistical principle, you can calculate the total measured variance. We talked about these, right. So true variance within the sample, there will be variance from sampling itself, and there will be variance from the instrument that we use for characterization, right. So ideally, the sampling and analysis variance should be low, or should be easily controlled, or should be 0. Only you're characterizing the true variance within the sample, but it doesn't happen all the time, right. But again, you can use those variance equations to calculate all these, total variance or measured variance from all these variance values. Again, I'm not going into that. Again, you can use simple variance calculation, variance equations, to use the, or to calculate the ideal minimum variance that you wanted to have when you are subsampling from the bulk powders. Okay. And we talked about sampling protocol, right? So initially when you develop a sampling protocol, so first you should know the characteristics of the material itself. Okay, we talked about free flowing and cohesive material, right? So first we should know the powder characteristics. If it's cohesive, very cohesive, like cake material, then you can just use a scoop for subsampling. Okay, it doesn't affect your characterization much. But if it's free flowing like rice grains, corn, cereal grains, then you will definitely need an appropriate sampling procedure, okay, that reflects their flow behavior or flowing characteristics. Because when it's flowing, they segregate, right? When it's free flowing, they segregate a lot. So again, determine the quantity of sample needed. Again, identify sampling technique, sample tool. Most often, in current industry scenario, it's limited by the system we have in the industry. It's not that we buy a new system. Usually, you might go and work for an industry, and your manager might say, "Oh, just use the scoop and get sample," right? So if they don't have any other advanced technique, but now you know why sampling is important, right? So you'll have to have a good sampling protocol. Again, prepare subsamples. Conducting homogeneity test, if you can at least, do some homogeneity test where the samples are mixed, uniformly, equally within the bulk, then it gives more, again, more representative characteristics of the materials. Okay? If it's not homogeneous, if you see lots of variation, then you will have to redevelop your sampling protocol. Somewhere, the method or equipment or sampling system that you are using may not be very valuable. Okay. So almost towards the end of sampling now, very common. That's what it happens. Except maybe in pharmaceutical industry. Pharma, again, as I said, it's low volume, high priced material, right? But in grain and food, it's like high volume, low priced. So we generally don't care a lot about subsampling, quality analysis, etc. But if for example, if you are working in a wheat flour mill, if the baker doesn't complain, okay, or a person who cooks roti or makes roti in home doesn't complain, then the wheat mill wheat mill engineer doesn't care or doesn't worry about it, right? So it doesn't worry about sampling or process manufacturing, etc. So if there is no problem for the downstream, if no one complains, then why cares or who cares? Okay. Again, that's what happens when you're dealing with like large volume, high volume, low, profit margin, industry like ag or food, etc. Okay. But when we go, if you're going by any chance, if you're going to work for a pharmaceutical company, then this will be a big challenge because they have very limited amount of samples to deal with. So then they should have a sampling protocol, sampling method, etc. Okay. Again, poor communication. Again, if you are working on the floor in the process, you may not know what the R&D group wants, right? So they might have different requirement than what you can do in the floor during manufacturing, and vice versa, right? So if you should have a good communication with other groups that are involved in the process manufacturing, from R&D till planning, etc. Okay. And again, better sampling. So proper sampling, again, as we saw, it's not very difficult to establish. It's very easy. You should know some statistics. You should have some some sampling equipment. Okay, simple sampling equipment. That's what you need to establish a sampling protocol. Okay, it's very easy to develop and very easy to implement. Okay. So keep in mind again, a couple of golden, we talked about the golden rules of sampling, right? The powder should be in motion, and then collect from the whole stream of flowing powder at many periods, many short duration than one bulk subsample. Okay. Again, if you are using some sampling devices, mainly understand the limitations. I showed one picture of pharmaceutical powders, right, with an N sampler. So if that is like periodically segregating powder, or if you are putting different powders in batches, then an N sampler might work better than a thief sampler with multiple pockets or multiple openings. Okay. So understand your process and understand your device that you use for sampling very well, so that you can so that you can develop good sampling protocol. Again, for subsampling, we always suggest the use of spinning rifflers. So you would have seen from that example, right, the variation from spinning riffler will be very low compared with other subsampling methods. Okay, I think that's my last slide. Any questions? Someone was happy when I said last slide. But again, if you are interested, there are tons of standards that you can follow. ASTM has many standards for sampling. British standards, ISO. You should be able to. I'm not sure if your library has access, but these standards may not be free to download, but if your library has access, you can download and use it. These are some of the references that I used in this lecture. Okay. Okay. Any questions? That ends our sampling part. Okay.
What if the statistical analysis gives us a large value of number for the samples, and we are dealing with high value component or high value material? Then can we reduce the number of samples?
Yeah. So in general, it wouldn't give large. So the the number n goes up when you tighten the standard deviation accuracy. So if it's like in the slide example that I gave, 0.01 gram per cc, right? So it's very tight. So if you are increasing your accuracy, like the number of samples needed will also go up. So you'll have to compromise somewhere. One compromise in the accuracy or compromise in the number of samples.